Starting us off in Chapter 2, we want to talk about atomic theory. So we've previously talked about the different classifications of matter. We know that we had this, kind of overall tree that, everything is matter. And, then at our next level, we could break that down into substances and mixtures, and we could break each of those down. Further, we had the different types of mixtures, and then we have the different types of substances. But at the end of the day, all of these mixtures, we know, are made up of substances. And then the substances that are either compounds or elements have to be made, it's either a compound, which is made of elements, or elements. So all of these different types of matter at their basic level are elements. So that leads to the natural question of, well, what are elements? And so we've touched on this idea that elements correspond to what we call atoms. Matter is made up of these small particles called atoms. So we have these really, really small particles, and they make up everything. We call them atoms. So what we're going to do is spend a little more time kind of formalizing what that means, or what we think about atoms and what atoms are and what their properties are. So each element corresponds to a type of atom. So when we say type of atom, we mean, we have a lot of different atoms out there. But if we have, say, oxygen, so that would be a gas. These are the red dots up top there. All oxygen, that's a type of atom. And so if you have any atom with those particular properties, we'd call it oxygen. And we would expect that all oxygen atoms have the same properties. That's what we mean when we say that they are consistent. And so it means oxygen's always the same. And then the other important property is that they are unique. So we could have a different element, for example, copper, that those atoms have different properties, right? They have their own unique properties that are different from the oxygen properties. But importantly, copper atoms are always the same. That makes them consistent. So if we want to make a compound, we make them out of elements. And what that means is that we have combined atoms of different types. So copper and oxygen are elements. They can come together to make a compound that's called copper 2 oxide. Not only would they come together to make that compound, but they'll always come together at a fixed proportion. It's going to be one copper atom for every one oxygen atom. And it's always going to be exactly 1 to 1. So then for chemical reactions, atoms are going to be rearranged between substances. We don't create or destroy atoms. Instead, we just move atoms around. We change those proportions, either being totally isolated in the element form, or maybe 1 to 1, 1 to 2 in the compound form. Importantly, atoms are never created or destroyed. So those are the important aspects with respect to, their chemical reactions and the chemical definitions. But we also want to kind of get a sense of what atoms are, how they function, what they look like. And so one of the things about atoms is that they are extremely small. And so, humans didn't know or have this idea of what atoms are for a really long time. And the reason is because we were never going to see them. So one atom, or one penny, is about 200 million times larger than one atom. Okay, so in terms of size, kind of side-to-side distance. And so that ratio of sizes is the same as the ratio of a penny to the size of the moon, right, which is massive. And so, if you think about how much smaller is a penny than the moon, that is the same relationship as to how much smaller an atom is than a penny. So these things are really, 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 really small, and we're never going to be able to see them, but they're going to have really important implications for how chemistry happens. So when we talk about making compounds, we know we're going to have these combinations of different types of atoms coming together. And so what we make then is called a molecule. And so molecules are small, tightly bound combinations of atoms. So, when you trace down from elements, eventually you find an atom, right? That's the smallest object of that element. When you have a compound, similarly, when you trace down, eventually you'd find a molecule. Okay, so that would be, that when you look at, for example, water, that has 2 hydrogen atoms and 1 oxygen atom. And so whenever you have water, it is consistent, just like atoms. It's always 2 hydrogen atoms and 1 oxygen atom together in a molecule, and that has unique properties. It's not like any other compound with different atoms paired together. And so there's these different representations we have up here. We'll get into those as we move through the semester. We'll see some soon. Some of them we won't come back to for till the end of the term. But we can see that there is this kind of recipe and there is a physical object. So much the same way that atoms are the physical object that describe elements, molecules are the physical objects that describe compounds. So atoms have structure. A lot of times we've seen some descriptions so far where they just kind of look like circles or spheres. And the thing is, they are not just hard spheres. We kind of have this image of them like, ball pit balls, something like that, just hard plastic balls. That's not quite it. Instead, they have regions. There are 2 primary regions of an atom. You have the nucleus, which is the small dense center, and the electron cloud, which is all the space around the nucleus. So there's 2 main volumes. If we have this description or this kind of graph over here, the nucleus would be this middle part right here. And then everything else in the outside we can see is this electron cloud. And so we can see that there are these 2 regions. The nucleus is small and dense. This is all of the mass and none of the volume. Okay, so all the mass is here, but not the volume. The electron cloud, which is then all that extra space, is all the volume, but very little of the mass. So we have these 2 regions of the atom, and these regions are filled by what are called subatomic particles. So a subatomic particle, sub means below. So these are particles, these are little objects that make up or compose an atom. So they are inherently smaller than atoms, but they come together to make up atoms. And I do want to touch a little bit about this idea of size. That graphic that we saw for that image is a really standard representation of that you would see of an atom. But importantly, that's not what an atom actually looks like. It's good. It allowed us to actually see all the little particles. But functionally, when we say that a nucleus is none of the volume, we really do mean it. This graphic here on the right shows that kind of grayish smudge is the electron cloud. And then that dot in the middle is the nucleus. And so it's zoomed in. You can see right here what that nucleus looks like. So the length of the nucleus is about 1/100,000th of the length of the atom. And then you would cube that to get to volume. And so you can really see that it is really a tiny, tiny proportion of the volume of the atom. For the most part, it's an atom's volume, its actual physical size, is composed primarily of the electron cloud. All right, so we want to talk about where these subatomic particles fit in. So the nucleus contains 2 types of subatomic particles, protons and neutrons. And so the difference between them is that protons are positively charged. So pro means like, for, moving, like for as in like pro for something, approving of it. And so pro is positive, protons. And then neutrons, so neutr, right, neutral, corresponds to those being neutrally charged. They have no charge. They are not positive or negative. They also have mass. They are objects, so they have a mass. Because atoms are very small, the subatomic particles are even smaller. So in general, when we're talking about the mass of these subatomic particles, we're going to use atomic mass units, or we can see the abbreviation AMU. And 1 AMU is very, very small, 10 to the negative 24th grams. So that's why grams aren't really useful. That number is really small. But AMUs are really useful. The reason why we have this seemingly random definition of an AMU is that a mass of a neutron is about the same as the mass of a proton, and they are about 1 atomic mass unit. So as the name implies, atomic mass units, they are the mass units appropriate for measuring things in atoms. So protons and neutrons have about the same mass. For our purposes, we're going to say they're the same. Then the only difference between them is their charge. But otherwise, they're both in the nucleus, both have that same mass. So we can see on the graphic here that the red balls are the protons, you can see that positive charge, and the green balls are the neutrons. So they're still in the nucleus, they have the same size as the protons, but they don't have any charge on them. So electrons are then these little blue particles that are floating around the nucleus. You will note the nucleus, those subatomic particles are locked in. They're staying in the nucleus. They are, kind of in a set position in that nucleus, whereas the electrons are outside of the nucleus, and they are going to be free to move around. So they're here kind of shown on these tracks. They really are moving around in here. We'll get to what those tracks look like, where they are in a bit, but that's one of the first key differences. They are moving and they're on the outside of the atom. They're also negatively charged. You can see the line right there. So not only are they negatively charged, but they are equal and opposite of the charge of the protons. So protons are +1 and electrons are -1. They have a very low mass, so 0.0005 AMU. It's not zero. They do have a mass. They are objects, but importantly, they have a much, much lower mass than protons and neutrons. Remember, protons and neutrons are 1 AMU, and these are 0.0005 AMU. So they are much, much smaller. That's why we say that the nucleus contains all of the mass, because protons and neutrons are so much bigger than any of the electrons. Importantly, electrons are on the outside of atoms. What that means is if you have two atoms that are going to interact with each other, which is how chemistry happens, that is going to be mediated by the electrons that are on the outside of the atom. That outside of the atom is how those electrons are how you get that interaction between two atoms. So electrons are going to be the driving factor for chemistry.